Today I'm going to show you how to verify your circuit analysis for a transient analysis of RLC circuit problem using LTSpice. The circuit that is shown on the screen is the circuit that was analyzed in my lecture on the total response of RLC circuits. So if we want to check what our calculations, or if we want to check if our calculations for the initial conditions are correct, what we could do is set up our circuit, which I've done, and then run what is called a DC operating point analysis. If we run this simulation, we see that the voltage at node 1, which is our voltage source, is 12 volts. The voltage at node 2, which is this node between resistors R1 and inductor L1, is 10.0003 volts. The voltage at node 3 is 9.99833 volts. And then we're also given a list of all the currents. This doesn't exactly match our analysis. And the reason for this is a problem with LTSpice. If we right-click on our inductor component, it tells us that the series resistance of an inductor defaults to 1 milliohm. 1 milliohm is 1,000 times smaller than the resistors in this circuit, but it's still enough to cause a little bit of variation. So what I'm going to do is I'm going to explicitly say the series resistance of my inductor is 0 ohms, making it an ideal inductor, and rerunning my simulation. Now I see that my voltage drop over my capacitor is exactly 10, which is what we got before, and my current through my inductor is 2 amps, which is exactly matches our calculations. So this is how you can do the initial conditions. The significantly more difficult part is matching your calculations for the transient analysis. And so what we're going to do is, for instance, in this circuit, during the transient condition, this 5 ohm resistor is removed from the circuit because there was a switch that opens up. So I'm just going to cut out this wire, which is going to do the same as opening that switch. And now I'm going to set initial conditions for my capacitor voltage and my inductor current. I do that by clicking on this .op button. And to set my initial condition, I do .ic, and then for the inductor current, it will be I, open parentheses, L1, because I'm setting the current of inductor L1, and it should be 2 amps. So I hit equals 2. Control M lets me do a new line where I'm going to do .ic, the voltage at node 3, which is the voltage where my positive polarity terminal of my capacitor is equal to 10 volts, which is the initial condition that we got. Drop this in. And now I'm going to do what's called a transient analysis. Because alpha for this circuit was 1 Nepper per second, I'm going to let this simulation run for about 10 seconds so that it's guaranteed to be long enough so that my values will settle to their final value. So if I run this simulation, hit the run button, and click on this voltage probe for my capacitor voltage, this is the shape of my response. So we see that it starts at 10 volts and it settles to 12 volts after a significant amount of time has passed. I can verify my simulation by right-clicking on this graph and hitting the Add Trace button, and it will allow me to type in a mathematical expression. So the mathematical expression that we got for our capacitor voltage in this example problem was -1 times T. In LTSpice, you have to explicitly write out time, times the exponential, so I'm going to do exp, of negative alpha, so -1 times time. Then we had A2 was -2 volts, so -2 times the exponential of -1 times time. And then finally, at t is equal to infinity, we had to put in our 12-volt term. And we can see that the blue curve has completely overlapped the green curve. So the mathematical expression that I have written completely matches the voltage waveform seen at node 3, which is the voltage drop over the capacitor. Sometimes they may look slightly different, so you need to make sure that your scale is the same on both sides. So here we're ranging from 10 volts at our bottom to 12 volts at the top, and here we're ranging from 10 seconds to 12 seconds. The difference in units is just because I didn't include voltage per second for this guy or voltages anywhere in here. But we can see that they're on the same scale and the graphs perfectly match each other. So my analytical solution using circuit analysis techniques matches the simulation. Thanks for watching.